Hello. In last lecture, you have learned how Maxwell equations can be solved in free space and in dielectric medium to show that light is an electromagnetic wave. Now we shall solve them in a conducting medium. Here I wish to mention that an electromagnetic wave in a conducting medium means an alternating current. But before proceeding further, we start with defining a conducting medium. For this, we shall discuss few properties of a conducting medium. The first one is Ohm's law. According to Ohm's law, the current density in a conductor is directly proportional to the electric field applied to flow the current. The proportionality constant is known as conductivity of the medium. Now multiply both the sides by length of the wire L and divide by the conductivity. Here E into L is a voltage applied across the wire length. Now the equation takes well-known form V equal to IR, where R is 1 by sigma L by A. 1 by sigma is defined as resistivity of the wire, rho. So this is the Ohm's law, followed by the conducting medium. Next, we shall see how charge behaves in a conductor. A conducting medium is defined by a zero charge density. Do you believe? Let a conducting medium is given a charge density rho. Now the continuity equation is the starting point. In this, J can be replaced using Ohm's law. So J is sigma E. And then divergence of E can be written using first Maxwell equation in terms of charge density rho. Now we get the integral equation for solution of charge density to get this solution. This equation indicates that as time passes, charge on the conductor decreases exponentially. Here, rho naught is the value of charge density on the conductor when time starts or at t equal to 0. The time after which rho naught reduces to 1 by E times rho naught is known as characteristic time t equal to tau. This tau depends upon the conductivity and permittivity of the medium, epsilon divided by the conductivity of the medium. It says that for a good conductor, the characteristic time is very less or a conductor is neutral practically. Because a conducting medium is neutral as a whole but has non-zero current density, Maxwell equation becomes like this. So, in case of conducting medium, we get an extra term containing J in fourth Maxwell equation. Now, to solve Maxwell equations in conducting medium, we follow the same method as we followed in case of free space. And that is, take curl of curl equations. Third curl equation gives this and this. Here J can be replaced by sigma E for conductor. So the final equation for electric field is this. Similarly, for magnetic field, the fourth Maxwell equation gives this equation. These are two equations for E and B containing double derivatives with respect to time and the space. Since these are the wave equations, so the solutions to them will be the wave solution of E and B like we had in case of free space and dielectric medium. Then what is the difference in this case? Let us discuss this. If you remember the wave equation in E and B for free space and compare them with those for conducting medium, then you will find this extra term with differential of the field with respect to time. And we need to find the effect of this extra term in case of conducting medium. For this, put the wave solution of E and B in the wave equations. By this, we get these equations for E and B, giving the relation for k square, which is a complex number. Because square of k is complex, so k will also be the complex number. We need to find the form of this wave propagation vector. Also, since k is related with E and B, a complex k vector indicates a phase lag between E and B in a conducting medium, which was 0 in case of free space and dielectric medium, because k vector in those cases was real quantity. So let k is written as a plus ib, a general form of complex number. Then k square can be written like that, which we had already found is equal to iota mu sigma omega plus mu epsilon omega square. So a square minus b square and 2ab get their values in terms of mu, sigma, omega and epsilon. By these relations, we can find the values of a and b in terms of omega, epsilon, mu and sigma. It is to be noted that for a very good conductor, sigma is very high, and for a poor conductor, sigma is very less. So, for a good conductor, a and b become equal to each other, and that is equal to under root of mu sigma omega by 2. And for a very poor conductor, sigma is very less than omega epsilon. So a and b get their different values, and these are given by a equal to omega under root epsilon mu, b equal to sigma by 2 under root of mu by epsilon. Maxwell's third equation reads del cross E equal to minus del B over del D. This can be solved by simply replacing del operator by iota k and differential operator with respect to time by minus iota omega. So this gives B equal to a plus iota b k unit vector divided by omega cross E vector. Because this equation contains complex quantity, there is a phase lag between B and E. Let us find this phase lag by representing the complex k vector in exponential terms. Any complex quantity can be written as the magnitude of that complex quantity, which is equal to under root of a square plus b square multiplied by exponential iota phi, where phi is phase angle for that complex quantity. This phase lag phi is given by tan inverse b upon a. For k vector, we already have the values of b and a for very good conductor and poor conductors. So the phi is pi by 4 for good conductor, because for a good conductor a and b are the same, and this phi is equal to tan inverse sigma by 2 epsilon omega for a poor conductor. After this discussion about consequences of complex wave vector on the phase relationship between E and B, let us put the value of k vector in our wave solutions of E and B, and this gives these equations, or these can be written like this also. Here exponential minus br, which contains no iota, can be put with the E0 and B0, which are the amplitude of electric field and magnetic field. So we got the different values of amplitude of E and B inside the conductor. Let us represent these different amplitudes, which are varying with R by a star on them. So E and B are written as these equations. Here E0 star and B0 star are the varying magnitudes of E and B, given by E0 exponential minus BR, B0 equal to exponential minus BR. Here R is the depth inside the material, R equal to 0 at the surface of conductor, R is greater than 0 inside the conductor. So the amplitude decreases exponentially as EM wave propagates inside a conductor. Here you can see that at the value R equal to 1 by B, the amplitude of E and B fields decreases to 1 by E times its value at the surface of the conductor. This distance is known as the skin depth in the conductor, because at a depth equal to 1 by B, the amplitude of EM wave will remain 1 by E part of that outside the medium. So amplitudes are attenuated as B or R increases. The distance it takes to reduce the amplitude by this factor 1 by E, about 1/3, is known as skin depth or the penetration depth, and is denoted by delta. So delta is 1 by B. For a good conductor, delta is under root of 2 by mu sigma omega, and for a poor conductor, delta is 2 by sigma under root of epsilon by mu. So because for a poor conductor, sigma is very less, so delta is very high, and this shows that electromagnetic waves can propagate easily inside a poor conductor. But for a good conductor, sigma is very high, so the delta is very less, and it says that in a good conductor, the electromagnetic waves cannot penetrate, or they can penetrate only up to a fixed distance of skin depth or the penetration depth. Also, delta depends for a good conductor on omega, which is the frequency of electromagnetic wave. So more the frequency, less the skin depth. So one can say that a good conductor behaves like a poor conductor for a very high frequency of electromagnetic wave or very high frequency AC. The typical value of skin depth for copper at 60 Hz AC is 8.6 mm, and this is the typical frequency in our houses. We use all the wires less than this 8 mm thickness, so copper is good enough in the wiring of homes. But as the frequency of AC increases to 1 GHz, the delta for copper reduces to 67 micrometer. And this says if we are using the copper wire for very high frequency, we need to use copper as thin as 67 micrometer, otherwise we are going to increase the cost of our instrument unnecessarily. Therefore, a direct current flows through the whole volume of a conductor and an alternating current flows only on the surface of the conductor as the conclusion. So in this unit of electromagnetic waves, what we have learnt is the differential and integral calculus of vector fields and scalar fields, the fundamental laws on which electromagnetism depend, 4 Maxwell equations which were given after the modification of Ampere's law by Maxwell. And then we have solved Maxwell equations in free space. By this we came to know that light is an electromagnetic wave. We also solved electromagnetic waves in a dielectric medium and found the refractive index of the medium. Then at last we solved the Maxwell equations for a conducting medium and the concept of skin depth was studied.